Is anybody else feeling a little cold? I think I feel like I'm freezing to death. Is that the light? I see it. I see the light. It's getting closer. I think this is the end. No, it's not a light, but it's warm. It's bright. It's a function. Oh, functions, how they fill my heart with joy, my spirit with hope, and my life with warmth. Dare I say it, these functions have found me on the brink of death, imbued me with strength, and brought me back to life. And now that we're nice and warm and cozy, let's hop right back into our discussion from last time and keep chatting about some function basics, class 10.2. Now we know that functions take input values and assign them to specific output values. Considered together, if we pair up those inputs and outputs, we can now start to identify some points. And those points don't just live nowhere, they live on the graph of our function, which we define as follows. Well, our graph is just going to be the collection, or in other words, the set of all of those points that we find. We write them as ordered pairs, where our x value is still that independent variable x, but our dependent variable f of x is now filling up that y slot. But those f of x's, they aren't coming from nowhere. We know that we get them from our x values. The way that we'd write that, and here's a little bit of new math terminology for you, is as follows. We'd say here that these values of x are in the domain. And the way that we'd write that is using this math symbol here that looks kind of like an E. This symbol literally means that x is an element of the domain. So it's one of the objects in that set. More informally, this symbol can really just mean that x is in the domain. And when I take that value of x in my domain, it is assigned by my function rule f to some value f of x that is an element of or belongs in that set of output values, which we call our range. Now, we'll talk about building graphs at a later point. Right now, I want to know if I have a graph, how do I go about determining whether or not it's a function? And there's something important that we need to remember about how a function maps values before we can understand the two tests that we will discuss. What is the criteria that we establish that distinguishes a function from a relation? What criteria must a relation meet in order to be a function? Take 10 seconds, go. Alrighty, well, you may remember that the thing that's unique about functions is that every input value x goes to exactly one value of y, or interchangeably of f of x, right? It would never go to two different places, which means if I think about this in the visual dimension, a test that I can use to determine whether a graph is in fact a function is one called the vertical line test, sometimes abbreviated VLT. Not expecting you to guess this, but take a guess. How do you think that a vertical line would intersect with a graph if each value of x can only go to one value of y? Take a risk, take a chance. What do you think about how a vertical line would interact with this graph? Go! Alrighty, let's see what you came up with. It turns out that the vertical line test says that a graph of a function needs to meet the following criteria. If I were to take any vertical line through any value of x on my graph, in other words, any vertical line that I draw through my graph, as it turns out, that line can intersect the graph of my function at exactly one place. The way that we'll write that is that we'll say that we can intersect the graph of a function at no more than one point. Let's use it, and then from our exploration, we'll see if we can figure out why it makes sense. Look at A here. I have the graph of a parabola like we were building back in Unit 8. The vertical line test says if I can take any vertical line and draw it through my graph such that those vertical lines only intersect at a single point, then I do indeed have the graph of a function, so we can confirm that parabolas are indeed functions. Try out the vertical line test with B and C here, this circle and that kind of squiggle shape. Tell me if it's a function, and then once you've got it, make a guess as to why you think the vertical line test actually works in telling me whether I've got a function on my hands or not. Go ahead. Alrighty. Well, for B, right, I can get away with only drawing one vertical line. Maybe I draw it here. Notice that this vertical line intersects twice, which is more than once, so a circle cannot be a function, it is just a relation. But for this squiggle C, anywhere where I draw a vertical line, no matter where I drop it, I hope you can see that I'm only crossing the graph at a single point. This guy is indeed a function by the vertical line test. Now, to make sense of why the vertical line test works, let's look back at that circle. If I think of the points where that vertical line intersects the graph, remember that a vertical line has an equation of x equals some number. Here it happens to be -2. That means that both of these points have the same x value going to different values of y. That means in context, I have an input x that maps to two different outputs y. That cannot be a function. It does not meet my criteria. Beautiful. But let's say that rather than given a graph, I'm just given a couple points. Well, the abstracted version of the vertical line test we call the coordinate test. Using that discussion from above, what do you think the coordinate test would tell me needs to be true about any collection of points if it's going to represent a function? Take a risk, take a chance. Tell me what you think. Go. Alrighty. Well, the coordinate test would say, right, if every x can go to only one y, all of the x values that we see in our collection of points should appear no more than once. Logically, if I have an x value that shows up twice, that means I have an input that's going to two different outputs. That cannot give me a function. Use your 3 down here. Try out the coordinate test. Tell me which of these examples are functions and which of them are just relations. Give it a shot. Alrighty. Well, looking at A, I have 0, -1, 2, and -3 in my x slot. Here, all of those are distinct inputs, so it doesn't even matter where they're going. I can say, yes, absolutely, this is a function. Same thing for B, -7, -8, 4, and 7. These are all different numbers, so they're all distinct inputs. This is a function. But if I flip those around, notice here now my x values are 4, -7, -8, and +4. Looking at that first and last point, that tells me that the input of 4 goes to both -7 and +7. That is impossible. It cannot be a function. Beautiful. So now that we have the graphs of our functions, we can now also start to think about identifying the characteristics of those graphs. Some of them should already be familiar to us, right? We've already defined our domain and range as our set of input and output values, respectively. Within the domain, we also have x-intercepts. Within the range, we also have our y-intercept. We have also talked in the past about identifying where graphs are increasing and decreasing. Look back in your notes here. Can you flesh out these definitions for me? What is it exactly that I'm interested in saying about my graph? Go. All right. Well, within my domain, my x-intercepts, sometimes you might remember, are interchangeably called the roots, and for functions, we often call them the zeros. These are going to be the value or the values of our variable x when we plug in 0 for y, which we write as f of x for functions. Flipping that for our y-intercept, right, this is going to be the value of y, which we'll write as f of x, when we plug in and evaluate 0 for x. Increasing and decreasing tells me where my graph is going up or down from left to right. I am increasing as the values of my function, right? So my y values are going up from left to right. And I would be decreasing when I'm doing the opposite. I'm going to use some quotes here just to save some time, right? I'm using exactly the same language as above, so I'm just bringing it down. The only change is that now we're going down as we read from left to right. But there is a secret third option that we'll see. Maybe I'm going up. Maybe I'm going down. But it's also entirely possible that my values could be staying the same. When that's the case, the math word that we'll use here is that we'll say that our values are remaining constant. So rather than going up or going down, the values of y, or f of x, are going to stay the same as we move from left to right. Let's get a little bit of practice with identifying some of these characteristics. We'll start with some graphs here. I've got part of a parabola for a, and a piecewise function like we briefly alluded to last time for b. Let's identify some domains and ranges, some increasings, decreasings, and constants, and then see if you notice anything that's a little bit different about how we might identify these characteristics from the last time we were working with them. Try it out. Alrighty. For the one on the left here, this part of a parabola, the thing that's different is that my domain is no longer all real numbers. If I want x values, I'm looking left and right. Notice that there are limits on how far left and right I can go. So for my domain, I'll express all of these in set builder, and for b, I'll use interval. Notice that my values of x are bounded by -2 on the left and +2 on the right. The way that I would write this is actually using a compound inequality like we would back in unit 2. X is sandwiched between -2 and 2, so it is greater than or equal to -2 and simultaneously less than or equal to +2. For my range, I'm talking about y values, which is up and down. Notice here, for my values of y, which we'll write as f of x, the limit here is that at the bottom, the lowest I can get is -4, and at the top, the highest I can get is +5. Now for increasing, decreasing, and constant, we've once again got some limits. Notice here that I am increasing, if I were to imagine that I have this invisible axis of symmetry, to the right of where that axis of symmetry would be. But I'm not increasing all the way off to infinity. Here, my values of x are increasing or creating increasing values of y when I am to the right of -1 and when I am to the left of that value of 5. Or not 5, sorry, but 2, right? That's where I cap out going left and right. And I'm decreasing here on this part of my graph, which I'll shade in blue. So here, again reading from left to right, I need to be bigger than that -2 where I'm at my limit. And then I need to be smaller than that -1, which is where my axis of symmetry would be. Now, the nice thing about this parabola is that it is not constant anywhere. The way that we would indicate that is by saying something like NA, not applicable, nowhere on this graph are we constant. Let's try B as well, and I'll use interval notation for this guy. For my domain and my range, again, domain is asking for left and right. So I have a lower limit here going left at 1, 2, 3, -4, and an upper limit going right at +3. So for values of x, that tells me here that my domain extends from -4 all the way on the left to +3 all the way on the right. For my range, right, these are my limits on up and down. Notice here that I'm capping out at the bottom at a value of -2 for y and at the top at a value of positive 4. Now for increasing and decreasing, once again, I'll kind of shade some stuff in. Notice this part of my graph goes up from left to right. Here, again, never included for increasing, so I'm going to use parentheses in interval notation. I start on the left at that x value of negative 4, and I stop increasing at the x value of negative 1. I am decreasing here for this branch, which I'll shade in blue. That goes from the x value of negative 1 on the left to the x value of positive 1 on the right. And now I do have a place where my graph is constant. That's when I'm to the right of that positive 1, but to the left of that upper limit of x equals 3. Last but not least, let's get a little bit of practice identifying some intercepts. So I have a linear function and I have a quadratic function. I want to find both the y-intercept and the zeros. Again, zeros are a fancy way to say my x-intercepts. Give yourself a little bit of time. Let's find some points on our axes. Go! Okay, well for g of x, let's start here. To find my y-intercept, again, the choice that I make is I'm going to plug in 0 for x. So I've got g of 0 that I need to evaluate if I'm using that function notation, which would be 15 minus 6 times 0. Well, 6 times 0 is just 0. This guy cancels out, and it leaves me with 15. As a point, I plugged in 0 for x. I got out 15 for g of x. Here is my intercept. Now I need to find the zeros. Again, zeros are just a fancy way to say that I'm working with x-intercepts. The way that I do that is by making the function itself here, g of x, equal to 0. So now I'm going to substitute in. 0 is equal to 15 minus 6x. If I solve for x, I should be able to get those points on my axis. Subtracting 15 from both sides here reveals that negative 15 is equal to negative 6x. My last move would be to divide both sides by negative 6. On the right, that leaves me with x, and if I simplify my fraction on the left, I should get positive 5 over 2. In context, again, I want to point on my graph. My x value is 5 over 2. It came from the y value of 0. Here is my x-intercept. Let's try it again. For h of x equals x squared plus 3x minus 28. Again, the choices that we make are exactly the same. To find my y-intercept, I'm going to begin by plugging in 0 for x. So h of 0 is what I'm evaluating, which would be 0 squared plus 3 times 0 minus 28. Again, 0 squared and 3 times 0, both of these are 0. I can functionally ignore them. So my y-intercept should appear at the point 0, comma, negative 28. And last but not least, to find my zeros, which again is just my x-intercepts, I'm going to take my function h of x and set that guy to 0. So from here, I've got 0 is equal to x squared plus 3x minus 28. Well, look at that. There's a quadratic trinomial. I know how to factor and use my 0 property. Well, x squared plus 3x minus 28, at the front it's got to be x times x. At the back, two numbers that multiply to get negative 28 and add to get positive 3 would be positive 7 and negative 4. And from here I'm home free. I can use my 0 property to split up and solve for x independently. If x plus 7 is equal to 0, minusing 7 from both sides would reveal that x is negative 7. And if I add 4 to both sides in the equation on the right, x could also be positive 4. Last but not least, I'll write these as my ordered pairs because once again I want points on my graph. That tells me negative 7, 0 and 4, 0 are the points on my x-axis.